A rocky planet that shouldn't exist just broke every rule we thought we understood about how worlds survive. The James Webb Space Telescope found an atmosphere where nothing should remain, a thick blanket of gases clinging to a world that orbits its star in just 10 hours, closer than any planet should dare to exist, bathed in radiation that should have stripped away every molecule millions of years ago. This discovery changes everything we thought we knew about planetary survival. The planet is called TOI 561b. You've probably never heard of it, but after today, you won't forget it. This world is roughly twice Earth's mass, spinning around a star so ancient it formed when the universe was barely a quarter of its current age. That star is located in a region of our galaxy called the Thick Disk, where metal-poor stars from the early universe still drift through space like cosmic fossils. And orbiting that ancient sun, at a distance 40 times closer than Mercury orbits our own star, is a planet that defies explanation. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Here's what makes this discovery genuinely unsettling. TOI 561b completes an entire year, one full orbit around its star, in 10.5 hours. Not days, hours. While you sleep through a single night, this planet experiences an entire year. The implications are staggering. Any world orbiting that close should be a barren rock, its surface blasted clean by stellar radiation, its atmosphere long since evaporated into space. Every model we've built, every simulation we've run, tells us the same story. Small rocky planets this close to their stars cannot hold on to atmospheres. They're too hot, too exposed, too vulnerable. The James Webb Space Telescope proved those models wrong. Over 37 hours of continuous observation, watching TOI 561b complete nearly 4 full orbits, Webb's instruments detected something that shouldn't be there. Temperature readings that didn't match predictions, thermal signatures that required explanation. The day side of this world, the hemisphere forever locked facing its star in perpetual scorching daylight, should register temperatures approaching 4,900 degrees Fahrenheit. That's hot enough to vaporize rock, hot enough to turn metals into gas, hot enough that nothing we call an atmosphere should survive. But Webb measured something different. The dayside temperature came in around 3,200 degrees Fahrenheit, still unimaginably hot by any human standard, but crucially, not as hot as it should be. That 1,700-degree difference tells a story. Heat is being redistributed. Something is carrying thermal energy from the blistering day side to the frozen night side. Something substantial enough to move heat across an entire planetary surface, despite the extreme conditions. That something is an atmosphere. Not a thin wisp of gas barely clinging to existence. Not trace amounts of molecules detected at the edge of our instrument's sensitivity. A thick, substantial atmosphere capable of redistributing heat across a world where the temperature difference between permanent day and permanent night should be measured in thousands of degrees. An atmosphere that by all rights shouldn't exist, persisting in conditions that should have destroyed it billions of years ago. The Discovery team calls it the strongest evidence yet of an atmosphere around a rocky exoplanet. That careful scientific language masks something profound happening beneath the surface of this finding. We found atmospheres around gas giants before. we've detected thin envelopes around larger super-Earths. But TOI 561b represents something new, a relatively small rocky world, twice Earth's mass, but far from the largest exoplanet we've discovered, maintaining a substantial atmosphere in conditions that should make atmospheric retention impossible. What's keeping that atmosphere in place? The answer appears to be as strange as the discovery itself. Scientists believe TOI 561b might be what they call a wet lava ball. Imagine a planet-wide ocean, but instead of water, the entire surface is molten rock, not solid crust with volcanic regions, not patches of lava flows. A complete global magma ocean, churning and flowing, covering every square kilometer of the planet's surface. And that magma ocean is in equilibrium with the atmosphere above it. Gases bubble up from the molten interior, feeding the atmosphere from below. The atmosphere in turn gets pulled back down into the magma ocean, absorbed into the churning rock. It's a cycle, a continuous exchange between the planet's surface and its gaseous envelope. For this process to work under such extreme conditions, TOI 561b must be extraordinarily rich in volatile compounds, the elements and molecules that readily turn into gases, far richer than Earth. The planet's composition suggests it formed in a chemical environment completely unlike the one that created our solar system. That chemical difference makes sense when you consider the star's age. TOI 561 is twice as old as our Sun, formed at a time when the universe contained far fewer heavy elements. In the early cosmos, before generations of stars had manufactured and scattered metals through supernovae, planetary systems formed from a different recipe: less iron, less silicon, different ratios of oxygen and carbon. The planets that condensed from those primordial clouds would naturally have compositions unlike anything in our neighborhood. TOI 561b might be showing us what planets looked like in the ancient universe, a window into planetary formation as it happened 10 billion years ago, when the cosmos was young and metal poor. That alone would make this discovery remarkable. But there's more to the story, and it gets stranger. The planet is tidally locked, one face perpetually pointed toward its star, the other in eternal darkness. This configuration is common for worlds orbiting so close to their suns. The star's gravity essentially breaks the planet's rotation until one hemisphere freezes in permanent daylight. For most tidally locked planets, this creates extreme temperature gradients. The day side bakes, the night side freezes. Without substantial atmospheric circulation, these worlds should develop temperature differences spanning thousands of degrees between their light and dark hemispheres. That's not what's happening on TOI 561b. The atmosphere is moving heat. Not perfectly. The day side is still far hotter than the night side, but efficiently enough to lower the day side temperature by 1700 degrees. That requires powerful atmospheric circulation, strong enough to overcome the planet's extreme temperature gradient and the intense stellar radiation, constantly trying to strip gases away into space. Think about what that means. This atmosphere isn't just surviving, it's dynamic, active, circulating with enough force to transport heat across a planetary diameter in a matter of hours. The winds on TOI 561b must be absolutely ferocious, driven by temperature differences that would make Earth's strongest hurricanes look like gentle breezes. And those winds are moving through an atmosphere thick enough to carry significant thermal energy, despite the planet's crushing proximity to its star. The density measurements add another layer to this puzzle. TOI 561b has unusually low density for a rocky planet of its size. When astronomers first characterized this world, before Webb's observations, that low density raised questions. Rocky planets should be dense, compressed iron cores surrounded by silicate mantles and crusts. But TOI 561b's density suggested something different. Either the planet contained more light elements than expected, or its structure deviated from standard rocky planet models in some fundamental way. The atmosphere discovery helps explain that density anomaly. If the planet is extraordinarily volatile rich, if it contains huge amounts of elements that readily form gases, then naturally it would be less dense than a similar planet made primarily of rock and metal. The atmosphere isn't just a thin shell around a conventional rocky planet. It's an integral part of the planet's structure, a substantial component of its total mass. Strip away that atmosphere, and you'd be removing a significant fraction of the planet itself. This raises an obvious question. How has that atmosphere survived? Stellar radiation at TOI 561b's orbital distance should be intense enough to photoevaporate atmospheric gases over time. High-energy photons from the star slam into atmospheric molecules, giving them enough energy to escape the planet's gravitational pull. Over millions of years, this process should erode even substantial atmospheres, leaving nothing but bare rock behind. Yet the atmosphere persists. The magma-ocean equilibrium provides part of the answer. If gases are continuously bubbling up from the planet's interior at the same rate they're being lost to space, the atmosphere could maintain a steady state. But that requires the planet's interior to contain vast reserves of volatile materials, more than we typically associate with rocky planets. The interior must be actively replenishing atmospheric losses through geological processes we're only beginning to understand. There's another possibility, one that several researchers have suggested. Perhaps we're wrong about atmospheric loss rates. Our models are based on observations of our solar system and theoretical calculations about how stellar radiation interacts with planetary atmospheres. But those models might not capture the full complexity of what happens in extreme environments. Maybe thick atmospheres can develop protective mechanisms we haven't accounted for. Maybe the interaction between a magma ocean and its atmosphere creates stability we didn't predict. Or maybe TOI 561b is younger than we think. Not in absolute terms. The planet must be ancient, given its host star's age. But in terms of its atmospheric history, perhaps the atmosphere we're observing formed relatively recently through some catastrophic event. A massive impact that released enormous quantities of volatiles from the planet's interior. A period of intense volcanic activity that outgassed enough material to rebuild what stellar radiation had previously stripped away. If the atmosphere is young, it might not have had time to erode yet. Each explanation raises new questions. If the atmosphere is being continuously replenished from below, what does that tell us about the planet's interior structure? If thick atmospheres can survive in these conditions better than we thought, what does that mean for our understanding of planetary evolution? If the atmosphere formed recently, what triggered that formation, and will we see similar events on other worlds? Webb's discovery of TOI 561b's atmosphere represents more than just finding air around one unusual planet. It challenges fundamental assumptions about planetary survival in extreme environments. For decades, astronomers have operated under the principle that small rocky planets close to their stars are essentially dead worlds. Baked, irradiated, atmosphereless rocks with no chance of maintaining the kinds of gaseous envelopes that make planets interesting. TOI 561b forces us to reconsider that assumption. If atmospheres can persist in these conditions, even temporarily, then the universe might contain far more dynamic rocky worlds than we imagined. Planets we dismissed as too hot, too close, too exposed, might actually harbor substantial atmospheres with complex chemistry and active weather systems. The implications for planetary diversity are profound. Every ultra-hot rocky planet becomes a potential target for atmospheric characterization. Every world we thought was a barren rock might surprise us with unexpected complexity. The technical achievement behind this discovery deserves recognition. Webb observed TOI 561b using its near-infrared spectrograph, watching the planet's thermal emission as it orbited its star. The telescope had to detect incredibly subtle temperature variations in infrared light, separating the planet's faint glow from the star's overwhelming brightness. Over 37 hours of observation, through nearly 4 complete planetary years, Webb's instruments accumulated enough data to measure that crucial 1700-degree temperature difference that revealed the atmosphere's presence. That level of precision represents the cutting edge of what's possible in exoplanet science. We're not just detecting planets anymore. We're characterizing their surfaces, their atmospheres, their climates. We're measuring temperature differences between the day and night sides of worlds dozens of light years away. We're inferring atmospheric circulation patterns from thermal signatures. We're reconstructing the chemical composition of alien worlds based on how they absorb and emit different wavelengths of light. TOI 561b won't be the last world to surprise us. Webb is just getting started. The telescope has already observed dozens of exoplanets, and each new dataset brings potential discoveries. But this particular finding, an atmosphere where nothing should survive, represents something special. It's not just about one planet. It's about the possibility that our understanding of where atmospheres can exist is too narrow, too conservative, too limited by our experience with the handful of planets in our own solar system. The universe, it turns out, is more creative than our theories predicted. Planets find ways to maintain atmospheres in conditions we thought were prohibitive. They develop equilibrium states between their surfaces and their gaseous envelopes that allow both to persist despite extreme radiation and heat. They hold on to volatiles through mechanisms we're still working to understand. And when we point our most sophisticated instruments at these worlds, they reveal complexity we never anticipated. But TOI 561b isn't the only world challenging our assumptions about where atmospheres can survive. In fact, it's just the beginning of a story that gets progressively more unsettling as we examine what else Webb has found among the nearby stars. Because while this scorching lava world maintains its atmosphere through sheer volatile abundance and geological activity, other discoveries suggest something even more profound might be happening on certain rocky planets. Something that brings us closer to answering the question that haunts every exoplanet discovery. Could any of these worlds actually support life? That world is 48 light-years away. Its name is LHS 1140b, and it might be the most important planet Webb has observed. This isn't another hell world. It's not a scorching rock orbiting so close to its star that its surface melts into magma oceans. LHS 1140b orbits in the habitable zone, that Goldilocks region where temperatures allow liquid water to exist on a planet's surface. More precisely, it orbits a red dwarf star at just the right distance that, if conditions are favorable, liquid water could pool on its surface. Actual liquid water, the kind life needs. The planet is about 5.5 times Earth's mass and roughly 70% larger in radius. That puts it firmly in super-Earth territory, bigger than our world, but not so massive that it necessarily became a gas giant. When astronomers first discovered LHS 1140b back in 2017, using the MERTH project, they calculated its density and assumed it was probably a rocky world, dense enough to suggest a solid surface, positioned well enough to potentially maintain surface water, but refined measurements over subsequent years revealed something unexpected. The planet's density was lower than initial calculations suggested. Not dramatically lower, but enough to fundamentally change what kind of world it might be. Lower density meant less rock and metal, which meant more of something else. And when scientists ran the numbers, they arrived at a startling conclusion. 9 to 19% of LHS 1140b's mass might be water. Let that sink in. Earth's oceans contain about 0.02% of our planet's total mass. LHS 1140b could have nearly 1,000 times more water by proportion. This isn't a planet with oceans. This is a water world, potentially covered by ice hundreds of kilometers thick, maybe harboring a subsurface ocean beneath that frozen shell, or perhaps maintaining liquid water on its surface under the right atmospheric conditions. The question became, does it have an atmosphere? Webb turned its instruments toward LHS 1140b in 2024, using its near-infrared imager and slitless spectrograph to analyze the light filtering through the planet's potential atmosphere as it passed in front of its star. The data came back showing something intriguing but frustratingly tentative. Hints of nitrogen. Nitrogen itself isn't necessarily a biosignature. Earth's atmosphere is 78% nitrogen, but nitrogen doesn't directly indicate life. What nitrogen does indicate, however, is atmospheric stability. A nitrogen-rich atmosphere on a rocky planet in the habitable zone would be significant because it suggests the planet successfully retained or regenerated its atmosphere, despite the harsh radiation environment around red dwarf stars. Red dwarfs are notorious for their violent stellar activity, powerful flares and intense ultraviolet radiation that can strip atmospheres from planets, especially in the early stages of a star's life when activity is most extreme. If LHS 1140b has a nitrogen atmosphere, that means it somehow protected or replenished its gaseous envelope despite being bathed in radiation from a young, active red dwarf for billions of years. That's already remarkable. But there's more. The planet is tidally locked to its star, just like TOI 561b. One hemisphere perpetually faces the sun, while the other remains in eternal darkness. This creates extreme temperature gradients that would normally freeze any atmosphere on the dark side and superheat gases on the bright side, potentially causing atmospheric collapse or escape into space. Yet preliminary data suggests LHS 1140b maintains its atmosphere despite this configuration. Climate models predict something extraordinary for tidally locked water worlds with substantial atmospheres. The dayside would receive constant stellar heating, warming the ice or liquid water directly beneath the star's gaze. But instead of creating a uniform water world, the models suggest the planet would become what researchers call an eyeball planet, a world where ice dominates most of the surface, but a circular region on the dayside melts into liquid water, creating an ocean surrounded by frozen terrain. Current modeling indicates this ocean could be roughly 4,000 kilometers in diameter, about half the surface area of the Atlantic Ocean. And here's what makes this truly extraordinary. The temperature at the center of that ocean, if atmospheric conditions are right, could be around 20 degrees Celsius. Room temperature, comfortable, potentially habitable. But these are models, predictions based on assumptions about atmospheric composition and planetary characteristics we haven't definitively confirmed. The nitrogen detection remains tentative, hints in the data rather than definitive proof. Webb needs more observation time to confirm the atmosphere exists and to characterize its composition in detail. Therein lies the challenge. LHS 1140b's orbital geometry limits how often Webb can observe it. The telescope can only schedule a maximum of 8 visits per year when the planet transits its star from our viewing angle. Each transit provides a single data point, one measurement of how starlight filters through the planet's atmosphere. Building enough data to detect specific molecules requires accumulating dozens of these measurements. Researchers estimate it will take at least 1 more year of observations to confirm LHS 1140b has an atmosphere. Detecting carbon dioxide, which would provide crucial information about greenhouse warming and surface conditions, might require 2 or 3 additional years. That's if everything goes perfectly, if the telescope remains operational, if observation time gets allocated, if no technical issues arise, if the data quality remains high. This waiting period is agonizing for scientists who recognize what's at stake. If LHS 1140b does have a nitrogen-rich atmosphere and maintains liquid water on its surface, it would represent humanity's best opportunity to study a potentially habitable ocean world with current technology. Not potentially habitable in the distant future when we develop better instruments. Potentially habitable now, observable with the telescope already in orbit. But potentially habitable doesn't mean inhabited. That's a distinction people often blur when discussing exoplanet discoveries. Habitable means conditions allow liquid water and organic chemistry. Inhabited means life actually exists there. Those are vastly different claims requiring vastly different levels of evidence. Webb cannot detect life directly. It detects molecules in planetary atmospheres by analyzing how different gases absorb specific wavelengths of light. Some molecules could theoretically serve as biosignatures, gases that, if detected in sufficient quantities, might indicate biological activity. Oxygen combined with methane, phosphine in rocky planet atmospheres, or the most controversial detection Webb has made so far, dimethyl sulfide. That molecule appeared in preliminary data from K218b, another potentially habitable world Webb observed. Dimethyl sulfide on Earth is produced almost exclusively by biological processes, specifically by marine phytoplankton. Finding it in another planet's atmosphere would be extraordinary, potentially revolutionary evidence for extraterrestrial life. Except the detection on K218b remains deeply controversial. The signal is weak, barely distinguishable from noise in the data. Dimethyl sulfide can theoretically be produced through non-biological chemistry under certain conditions, though we've never observed those conditions creating DMS in our solar system. And K2-18b itself might not be the habitable world scientists initially hoped. Its classification as a Hycean world with a hydrogen-rich atmosphere and subsurface ocean remains debated, with some researchers arguing it's more likely a mini-Neptune with no solid surface at all. Follow-up observations using different instrument modes and longer integration times are currently underway. Those results will either confirm the dimethyl sulfide detection, refine it into something more mundane, or rule it out entirely. If confirmed with high statistical confidence, it would represent the strongest evidence yet for potential biosignatures beyond our solar system. If ruled out, it becomes a cautionary tale about the dangers of over-interpreting preliminary data. This is the reality of biosignature detection. It's extraordinarily difficult, fraught with ambiguity, and requires years of careful observation to reach definitive conclusions. Individual molecules rarely constitute smoking gun evidence. Context matters. Atmospheric chemistry is complex. Non-biological processes can produce surprising combinations of gases under the right conditions. What researchers really need is multiple biosignatures detected simultaneously, in combinations that would be difficult or impossible to explain through non-biological chemistry alone. Oxygen and methane together in a rocky planet's atmosphere would be compelling because those gases react with each other rapidly. Maintaining both simultaneously requires continuous replenishment, which biology can provide. Nitrogen, oxygen, water vapor, and trace amounts of gases like nitrous oxide or methyl chloride would paint a picture consistent with biological activity. But detecting that full suite of molecules requires observation time, telescope sensitivity, and favorable planetary characteristics that amplify atmospheric signals. Rocky planets in habitable zones around Sun-like stars are effectively invisible to Webb's current capabilities. Their small size and thin atmospheres create signals too weak to characterize. That's why researchers focus on super-Earths around red dwarf stars, where the planet-to-star size ratio is more favorable and atmospheric features appear more prominent in the data. Even then, obstacles abound. Red dwarf stars exhibit intense magnetic activity that creates hot and cold spots on their surfaces. When planets transit these stars, the starlight filtering through their atmospheres gets contaminated by these stellar inhomogeneities. Distinguishing actual atmospheric signals from stellar noise requires sophisticated statistical analysis and multiple observations to average out time-varying stellar features. TRAPPIST-1e exemplifies this challenge perfectly. This planet sits in the center of its star's habitable zone, among 7 Earth-sized rocky worlds orbiting a nearby red dwarf. Webb observed it 4 separate times between June and October 2023, and researchers immediately noticed heavy stellar contamination in the data. It took over a year of careful analysis to sift through the signals, comparing observations of TRAPPIST-1e with those of TRAPPIST-1b, an inner planet almost certainly too hot to maintain an atmosphere. The results present 2 possible scenarios. Either TRAPPIST 1e has a secondary atmosphere containing heavy molecules like nitrogen and methane, or it's a bare rock with no atmosphere at all. and what appears to be atmospheric signals is actually stellar contamination mimicking atmospheric features. The 4 observations obtained aren't precise enough to definitively distinguish between these possibilities. If TRAPPIST-1e does have an atmosphere, it would be momentous, the first confirmed atmosphere on a rocky planet in the habitable zone of another star. But confirming that requires more data, more observation time, more years of patient analysis. The astronomy community waits, knowing the next set of observations could either validate the tentative atmospheric detection or demonstrate it was stellar noise all along. This is where exoplanet science stands right now, on the knife's edge between transformative discoveries and frustrating ambiguity. Webb has the capability to detect and characterize atmospheres on rocky planets. It has proven that with TOI 561b and several other worlds. But extracting definitive answers about habitability and biosignatures from the data requires pushing the telescope to its absolute limits, accumulating observation time measured in years, and accepting that some questions might remain unanswered until the next generation of observatories comes online. Meanwhile, Webb continues its survey of potentially habitable worlds, adding new targets, refining observations of existing targets, building a database of atmospheric spectra that will shape exoplanet science for decades. Each new dataset brings potential surprises, potential disappointments, potential revolutions in our understanding of planetary atmospheres and the conditions necessary for life. But there's one world Webb has studied that challenges everything we thought we knew about where life might emerge. A planet so unexpected in its characteristics that its very existence forces us to reconsider the boundaries of habitability itself. LHS 1140b sits 48 light-years from Earth, orbiting a red dwarf star considerably smaller and cooler than our Sun. Discovered in 2017, this super-Earth initially attracted attention for its location, squarely within the habitable zone where liquid water could exist, but early observations left its true nature ambiguous. Was it a dense, rocky world? A water-rich mini-Neptune? Scientists couldn't tell. The planet's mass suggested something between those extremes, but precise composition remained elusive. Then Webb turned its infrared eyes toward this distant world, and the data began revealing something extraordinary. The spectroscopic observations ruled out a hydrogen-rich atmosphere almost immediately. That thick, puffy envelope characteristic of mini-Neptunes wasn't there. Instead, the data pointed towards something with higher mean molecular weight: nitrogen, water vapor, carbon dioxide. The kind of atmospheric composition that makes scientists lean forward in their chairs during presentations. By July 2024, tentative hints of atmospheric nitrogen emerged from the analysis, suggesting this world might possess the nitrogen-based air that would make surface oceans possible. Not certain, not definitive, but tantalizing enough to redirect observation campaigns and recalculate what this planet might actually be. Refined density measurements changed the entire picture. LHS1140b isn't primarily rock and metal like Earth. It's likely an ocean world with 9 to 19% of its mass composed of water. Think about that proportion. Earth's oceans represent less than 0.02% of our planet's mass. LHS1140b could contain 1,000 times more water, proportionally speaking. This isn't a world with oceans on its surface. It's a world where oceans define its very nature. The planet exhibits synchronous rotation, tidally locked with one face eternally turned toward its star. On Earth, this would create temperature extremes incompatible with life. The star-facing side would roast, while the dark side froze solid. But LHS 1140b's substantial water content changes that dynamic completely. Climate models suggest the star-facing hemisphere receives enough heat to melt surface ice in a specific region, creating what scientists call a bullseye ocean, a circular sea surrounded by frozen wasteland, giving the planet an uncanny resemblance to a cosmic eyeball. The dimensions of this potential ocean are staggering. Models indicate it could span 4,000 kilometers in diameter, equivalent to half the surface area of Earth's Atlantic Ocean. And the temperature at its center, possibly 20 degrees Celsius, room temperature, comfortable enough for liquid water, complex chemistry, and potentially the emergence of life. These aren't wild speculations based on wishful thinking. They're the output of sophisticated climate modeling that accounts for atmospheric composition, stellar radiation, and heat distribution patterns. But here's where scientific caution becomes essential. Those nitrogen hints, they need confirmation. Webb can only observe LHS 1140b8 times per year due to visibility constraints from its orbital position. Building enough signal-to-noise to definitively confirm the atmosphere requires at least one more year of observations. Detecting carbon dioxide with confidence? 2 or 3 additional years. The telescope must accumulate dozens of transits, stacking observations to amplify genuine atmospheric signals above the noise floor. Patience becomes mandatory when you're characterizing atmospheres on worlds dozens of light years away. The significance of LHS 1140b extends beyond this single world. If confirmed, it represents our best opportunity to study an alien ocean in detail. Not a world covered entirely in water like some science fiction concepts, but a planet where ice and liquid water coexist in configurations unlike anything in our solar system. The eyeball configuration itself poses fascinating questions. What happens at the boundaries between frozen and liquid zones? How does heat transfer through that global ice shell? Could life emerge in the temperate ocean region and spread to the twilight boundaries? This discovery also highlights a broader pattern emerging from Webb's observations. The most promising potentially habitable worlds aren't Earth analogues. They're super-Earths and mini-Neptunes orbiting red dwarf stars, configurations completely absent from our solar system. LHS 1140b, TRAPPIST-1e, and similar targets represent planetary types we never encountered during our exploration of our cosmic neighborhood. We're learning that habitability might manifest in forms radically different from what we see on Earth. Red dwarf stars dominate the galaxy. They outnumber Sun-like stars by roughly 20 to 1, and they'll continue burning for trillions of years after stars like our Sun exhaust their fuel. If planets orbiting red dwarfs can maintain atmospheres and surface water despite their stars' intense magnetic activity and frequent flaring, then the number of potentially habitable worlds in the galaxy increases by orders of magnitude. But if red dwarf activity strips atmospheres too efficiently, rendering planets like TRAPPIST-1b and 1c into barren rocks, then habitability becomes far rarer than optimistic projections suggest. The tension between these possibilities drives current research priorities. Every new observation of a red dwarf planet either strengthens or weakens the case for habitability around these ubiquitous stars. LHS 1140b's potential atmosphere argues for optimism. The planet orbits a relatively quiet red dwarf, but it still faces stellar activity far more intense than Earth experiences. If it retains substantial air despite that bombardment, other similar worlds might too. The alternative, that LHS 1140b is an outlier, an exceptionally lucky planet that somehow avoided atmospheric stripping, would be scientifically disappointing, but still valuable for understanding the limits of habitability. Webb's observations have also revealed unexpected complexity in how atmospheres respond to stellar environments. TOI 561b shouldn't have air according to conventional wisdom, yet it does. LHS 1140b might possess nitrogen-rich atmosphere despite orbiting a red dwarf. These surprises suggest planetary atmospheres are more resilient and diverse than theories predicted. Planets might retain air through mechanisms we haven't fully characterized. Volcanic outgassing, continuously replenishing atmospheric losses, magnetic fields we haven't detected protecting against stellar wind, or chemical processes that lock atmospheric gases into surface reservoirs during inactive periods and release them when conditions moderate. The eyeball planet configuration itself might be common for tidally locked worlds in habitable zones. If so, this completely reframes our search for life. Instead of looking for globally habitable conditions like Earth provides, we should search for planets with concentrated habitability, localized regions where temperature, pressure, and chemistry align favorably. Life might emerge in those habitable pockets and adapt to the extreme gradients between frozen darkness and the temperate zone. Or it might remain confined to narrow bands where conditions stay stable. K218b represents another world that challenges conventional thinking, though in ways more controversial than LHS 1140b. This subneptune orbits a red dwarf star 124 light-years away, and Webb's initial observations detected methane and carbon dioxide in its atmosphere, expected molecules that don't particularly surprise anyone. But the data also showed tentative signals of dimethyl sulfide, a molecule produced almost exclusively by biological processes on Earth. Phytoplankton in our oceans generate it. When it escapes into the atmosphere, it creates that distinctive smell associated with marine environments. The scientific community responded to the dimethyl sulfide detection with intense scrutiny and appropriate skepticism. Extraordinary claims require extraordinary evidence, and detecting a potential biosignature on an exoplanet definitely qualifies as extraordinary. The signal could be real. It could also be an artifact of data processing, stellar contamination mimicking a molecular absorption line, or a genuine detection of dimethyl sulfide produced through non-biological chemistry we don't fully understand. The planet's classification as a Hycean world, a hypothetical category of hydrogen-rich water worlds, remains debated, with some researchers arguing K218b might be too massive and its atmosphere too thick for surface oceans to exist. Follow-up observations using different instrument modes and longer integration times will either confirm, refine, or rule out the dimethyl sulfide detection. If confirmed at high statistical significance, it would represent the strongest evidence yet for potential biosignatures beyond our solar system. But even then, scientists would need to eliminate every possible non-biological explanation before seriously considering biological origins. The history of science contains numerous examples of apparent biosignatures that turned out to be geological or atmospheric processes mimicking life's chemical signatures. Mars meteorite ALH 84001, the phosphine detection on Venus, the methane variations in Mars's atmosphere, each generated initial excitement followed by deflation as alternative explanations emerged. The K218b situation underscores a fundamental challenge in biosignature detection. A single molecule, even one strongly associated with life on Earth, isn't sufficient evidence. Scientists need to detect multiple biosignatures simultaneously, oxygen and methane together, or methane with other organic compounds in ratios that defy non-biological explanation. They need to rule out geological sources like volcanic activity or photochemistry driven by stellar radiation. They need to demonstrate the molecules exist in abundances that require continuous replenishment, suggesting active biological production rather than trace amounts from ancient impacts or chemical reactions. That's an extraordinarily high bar to clear, and it requires observational precision that pushes Webb to its absolute limits. Yet these discoveries, even the ambiguous ones, demonstrate that Webb has moved exoplanet science into a new regime. Before its launch, detecting any molecules in rocky planet atmospheres seemed like a next-generation telescope problem. Webb has done it for TOI 561b. Before 2022, characterizing potentially habitable super-Earth atmospheres required speculation and extrapolation from theoretical models. Now we have actual data on LHS 1140b, TRAPPIST-1e, and similar targets. Before Webb, discussions of biosignatures on exoplanets remained largely theoretical. Now scientists debate actual detections and tentative signals, arguing about whether specific spectral features represent genuine molecular absorption or observational artifacts. The telescope's impact extends beyond individual discoveries to how scientists approach the entire field. Research teams now design observation campaigns spanning multiple years, knowing that definitive atmospheric characterization requires patient accumulation of data. They develop sophisticated statistical methods to distinguish genuine planetary signals from stellar contamination. They collaborate across institutions to pool expertise in stellar physics, atmospheric chemistry, climate modeling, and observational astronomy. The complexity of extracting meaningful conclusions from Webb's data demands interdisciplinary cooperation at unprecedented scales. And still, fundamental questions remain unanswered. Does TRAPPIST-1e have an atmosphere? Years of additional observations will resolve that uncertainty one way or another. Does LHS 1140b actually possess that nitrogen-rich air and temperate ocean? More data will confirm or refute the tentative detection. Is the dimethyl sulfide on K218b real? And if so, does it indicate biological processes? Future observations will clarify those signals. Each answer will reshape our understanding of planetary atmospheres and habitability. But each answer will also generate new questions that push against the boundaries of what current technology can address. The search for life beyond Earth has always been characterized by this pattern: tantalizing hints followed by ambiguity, requiring better instruments and longer observation campaigns to resolve. Webb represents a massive leap forward in capability, but it still operates at the edge of what's physically possible when characterizing small rocky planets around distant stars. The telescope can detect atmospheres on favorable targets. It can identify molecular constituents and measure temperature profiles. But definitive biosignature detection, the kind that would satisfy the scientific community's rigorous standards for claiming we've found evidence of extraterrestrial life, might require capabilities beyond what Webb provides. That reality doesn't diminish the telescope's achievements, it contextualizes them within the longer arc of astronomical discovery, where each generation of instruments answers some questions, while revealing new mysteries that demand even more powerful tools to investigate. Perhaps the most sobering lesson from Webb's first 4 years comes from understanding what the telescope was actually designed to accomplish versus what popular imagination hoped it would deliver. When NASA and its partners conceived Webb in the 1990s, they envisioned an infrared observatory optimized for studying the early universe, the first galaxies, the first stars, the cosmic dark ages. Exoplanet atmospheres were a secondary science goal, added to the mission objectives later as the field of exoplanet science exploded in the early 2000s. Yet public fascination fixated on Webb as the instrument that would finally answer whether we're alone in the universe. That expectation mismatch created inevitable disappointment when early results proved ambiguous rather than definitive. The telescope performs brilliantly within its design parameters, detecting molecules in exoplanet atmospheres with unprecedented sensitivity. But unprecedented doesn't mean sufficient for all questions. Webb can characterize hot Jupiters with relative ease. Those giant planets orbiting close to their stars generate strong thermal signals that Webb's infrared instruments readily detect. Sub-Neptunes present more challenges but remain accessible targets. Rocky planets in habitable zones, though. Those push Webb's capabilities to the absolute edge, requiring observation campaigns spanning years and analysis techniques that extract signal from noise at levels that would they seemed impossible a decade ago. Consider the resource allocation required for these campaigns. Webb operates as a shared facility, with observation time distributed among hundreds of research programs spanning all areas of astronomy. A single rocky exoplanet atmospheric characterization might consume 40 to 100 hours of telescope time spread across multiple years. That's time not spent observing distant galaxies, studying stellar formation, mapping the solar system, or addressing any of the countless other scientific questions competing for access. The Time Allocation Committee faces impossible choices. Approve the multi-year campaign that might confirm an atmosphere on TRAPPIST-1e, or distribute those hours among dozens of other worthy projects. The scientific community debates this resource allocation constantly. Some astronomers argue that definitively characterizing even one potentially habitable rocky planet's atmosphere justifies extraordinary time investment. Others contend that spreading observations across many targets builds a more complete understanding of atmospheric diversity. Still others suggest focusing Webb's remaining operational lifetime on targets where its capabilities provide clearer advantages. Hot Jupiters, warm sub-Neptunes, unusual atmospheric compositions, rather than pushing the telescope beyond its practical limits. These debates reflect deeper tensions within astronomy about how to balance discovery-driven science against systematic surveys. Webb excels at the former, pointing at specific targets and collecting exquisite data that reveals previously hidden details. But building comprehensive understanding of exoplanet atmospheres requires the latter, observing enough systems across diverse conditions that patterns emerge. One telescope cannot simultaneously provide depth and breadth, forcing researchers to make strategic compromises. The stellar contamination problem exemplifies these challenges in particularly frustrating ways. Red dwarf stars, the most common stellar type in the galaxy and the hosts of most known rocky exoplanets, are magnetically active, covered with dark star spots and bright faculae that create temperature variations across their surfaces. When a planet transits its star, the combined light Webb receives includes contributions from different parts of the stellar surface. If the planet happens to pass over a star spot, the measured spectrum changes not because of the planet's atmosphere, but because of the star's surface features. Disentangling these effects requires observing multiple transits and hoping the stellar surface features change between observations. If a spectral feature appears in some transits but not others, it's probably stellar contamination. If it appears consistently across many transits, it's more likely planetary. But this statistical approach demands extensive observation time, hence the multi-year campaigns. For TRAPPIST-1e, astronomers need enough transits to map the star's surface variability and then enough additional transits to detect the actual planetary atmosphere once they've accounted for stellar effects. The mathematics governing signal detection creates another fundamental constraint. Detecting a molecule in an exoplanet's atmosphere requires measuring the difference between the spectrum when the planet transits the star versus when it doesn't. That difference is typically tiny, parts per million or smaller. The uncertainty in any single measurement might be 10 or 100 times larger than the signal being measured. Only by combining many observations does the signal emerge from the noise with statistical confidence. But combining observations assumes the signal remains stable over time. For planets orbiting active stars, that assumption might not hold. If the stellar surface changes between observations, or if the planet's atmosphere varies seasonally or due to stellar flares, combining observations could actually reduce clarity rather than improve it. Researchers must develop sophisticated models that account for both stellar variability and potential atmospheric changes while extracting the underlying signal, a mathematical challenge that pushes the boundaries of statistical inference. These technical realities explain why confirmation takes so long. When scientists announce a tentative detection of an atmospheric component, they're typically reporting a signal at 2 or 3 sigma confidence, meaning there's roughly a 5% to 0.3% chance the signal is just noise. That's interesting, worth publishing, worth discussing, but it's not confirmation. Confirmation requires 5 sigma confidence or better, where the probability of the signal being noise drops below 1 in a million. Reaching that threshold for rocky planet atmospheres requires more data than Webb can collect in a single year, sometimes more than it can collect in several years. The operational constraints of Webb itself impose additional limitations. The telescope orbits the Sun-Earth L2 Lagrange point, maintaining a position that keeps Earth, Moon, and Sun behind its sunshield. This orbital geometry means Webb can only observe certain parts of the sky during specific times of year. Some targets like TRAPPIST-1 and LH S1140 are accessible for several months annually. Others have much more restricted visibility windows. If a target is only observable for a few weeks per year, building up sufficient signal requires a multi-year campaign simply because the telescope can't point at that part of the sky during most of the year. Instrument scheduling adds another layer of complexity. Webb carries 4 main instruments: NIRCam, NIRSpec, NIRIS, and MIRI. Each has specific capabilities optimized for different types of observations. Atmospheric characterization primarily uses NIRSpec and NIRISS for spectroscopy, but these instruments are in high demand for many research programs. Scheduling observations requires coordinating not just when targets are visible, but when the appropriate instruments are available, when guide stars are positioned favorably, when the telescope orientation allows the sunshield to protect sensitive equipment. Then there's the question of what happens when Webb's operational lifetime ends. The telescope launched with enough fuel for a 10-year mission, but precise trajectory corrections during deployment extended that to potentially 20 years or more. Still, Webb will eventually run out of fuel for maintaining its orbit, or critical components will degrade beyond repair. What happens to ongoing observation campaigns when that occurs? The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will provide some capabilities complementary to Webb, particularly for surveying large areas of sky to identify exoplanet candidates. But Roman's design prioritizes different science goals and won't directly replace Webb's atmospheric characterization capabilities. The next telescope comparable to Webb in atmospheric study capability, possibly the Habitable Worlds Observatory currently in early planning stages, likely won't launch until the late 2030s or 2040s. That creates a potential gap where ongoing atmospheric characterization campaigns might be interrupted for a decade or more. These practical constraints shape how astronomers approach their research strategies. Some teams focus on targets where definitive results seem achievable within Webb's operational lifetime. Others pursue longer-shot observations that might not yield confirmation but will constrain possibilities and guide future telescope designs. Still others work on improving analysis techniques, knowing that better algorithms might extract clearer signals from existing data without requiring additional observation time. The broader scientific community watches these efforts with mixed feelings. There's genuine excitement about what Webb has already revealed: atmospheres on planets that shouldn't have them, unexpected molecular compositions, hints of potentially habitable conditions. But there's also recognition that the next major advance in exoplanet atmospheric science might require capabilities beyond what Webb provides. What would those capabilities look like? Larger aperture, obviously. A bigger mirror collects more light and provides better signal-to-noise. But size isn't everything. Improved detector sensitivity, particularly in wavelength regions where key biosignature gases absorb light, would enhance detection capabilities. Better spatial resolution would allow direct imaging of planets rather than relying on transit spectroscopy, eliminating stellar contamination issues entirely. Coronagraphs that block starlight more effectively would enable observation of planets in wider orbits, including true Earth analogues around Sun-like stars. Some proposed missions aim for these capabilities. The Habitable Worlds Observatory concept includes a coronagraph designed specifically for direct imaging of Earth-like planets. The LUVOIR and HabEx mission concepts studied in recent years outline telescopes with 8-meter to 15-meter primary mirrors and instruments optimized for biosignature detection. But these remain concepts requiring decades of development and funding commitments that haven't yet materialized. In the meantime, Webb continues its observations, accumulating data that future scientists will reanalyze with improved techniques. The telescope's archive represents a permanent resource. Every observation is preserved and publicly available, allowing researchers to revisit targets with new insights or methods. Data collected today might yield breakthroughs years from now when someone develops a better way to extract signal from noise or correct for systematic effects. This archival value shouldn't be underestimated. Hubble observations from the 1990s are still being reanalyzed today, revealing details that original researchers couldn't detect with contemporary techniques. Webb's data will likely prove similarly durable, providing raw material for discoveries long after the telescope itself stops operating. That legacy justifies observation campaigns that might not produce immediate results, but build a foundation for future understanding. The question of what we'll ultimately learn about potentially habitable worlds from Webb remains open. The optimistic scenario has TRAPPIST-1e or LH S1140b yielding confirmed atmospheric detections within the next few years, providing the first definitive evidence of air on a rocky planet in the habitable zone of another star. That would be momentous, not proof of life, but proof that habitable zone rocky planets can retain atmospheres despite their star's radiation, a crucial prerequisite for habitability. The pessimistic scenario has stellar contamination and systematic effects, preventing definitive atmospheric characterization of any habitable zone rocky planet within Webb's operational lifetime. In that case, Webb's legacy in exoplanet science would rest on its characterization of hot Jupiters, warm sub-Neptunes, and unusual worlds like TOI 561b, still valuable, still advancing the field, but falling short of answering whether Earth-like atmospheres exist elsewhere. Most likely, the outcome falls between these extremes. Webb will probably confirm atmospheres on some rocky planets, while leaving others ambiguous. It will constrain atmospheric compositions, even when it can't definitively detect specific molecules. It will reveal that some classes of planets, perhaps those orbiting particularly active stars, remain beyond its characterization capabilities, while others prove more accessible than expected. Whatever the outcome, Webb's observations are redefining how astronomers think about the transition from detecting exoplanets to understanding them. Before Webb, knowing a planet existed and measuring its basic properties, size, mass, orbit, represented the state of the art. Webb has moved the field into an era where atmospheric composition, thermal structure, and potentially even surface conditions become accessible to observation, at least for favorable targets. That shift changes the questions astronomers ask. Instead of, are there rocky planets in habitable zones? The question becomes, do those planets have atmospheres? Instead of, do atmospheres exist? The question becomes, what are they made of? Instead of, what molecules are present? The question becomes, are those molecules consistent with biological production? Each answer leads to more sophisticated questions, driving the field toward ever more detailed understanding. This progression mirrors how astronomy has always advanced. Initial discoveries revealing that something exists, followed by decades or centuries of increasingly detailed characterization. Webb represents one step in that progression, neither the first nor the last, but a particularly significant one that expands what's knowable about distant worlds. The technical challenges Webb faces become clearer when you examine how the telescope actually measures atmospheric composition. The most powerful technique involves transmission spectroscopy, watching a planet pass in front of its star and analyzing how starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths, creating a chemical fingerprint. Sounds straightforward, but the signal is vanishingly small. For an Earth-sized planet transiting a Sun-sized star, the atmosphere blocks only about 1 part in 10,000 of the starlight. Detecting that requires extraordinary precision. Webb's instruments achieve this precision through careful design. The NIOSPEC spectrograph can split infrared light into its component wavelengths with remarkable resolution, measuring intensity variations of just a few parts per million. The MIRI instrument extends this capability into the mid-infrared, where many interesting molecules like methane and ammonia leave strong signatures. NIRCam provides broad wavelength coverage for initial surveys. Each instrument has specific strengths, and astronomers carefully choose which to use based on target characteristics and scientific goals. But instrumental precision only matters if you can separate planetary signals from stellar noise. That's where things get complicated. Stars aren't perfectly uniform spheres emitting steady light. They have star spots, cooler, darker regions analogous to sunspots on our Sun. They have faculae, brighter, hotter regions. These features rotate in and out of view as the star spins, creating brightness variations that can dwarf the tiny atmospheric signals from transiting planets. When TRAPPIST-1e transits its star, any star spots or faculae along the transit path affect measurements, potentially mimicking or masking atmospheric features. Disentangling these effects requires observational cleverness. Astronomers observe multiple transits, hoping stellar features change position between observations, while planetary atmospheric signals remain constant. They observe different planets in the same system, using airless worlds as controls to characterize stellar contamination. They build sophisticated models of stellar surfaces, trying to predict and subtract starspot effects. Each approach has limitations. Stellar activity can be unpredictable. Control planets might not perfectly represent conditions during the target planet's transit. Models require assumptions that might not match reality. The TRAPPIST-1e observations illustrate these challenges viscerally. 4 separate transits observed between June and October 2023 produced datasets that looked promising initially. Researchers saw spectral features consistent with atmospheric absorption, but when they examined the data more carefully, accounting for stellar variability, the interpretation became murky. Were those features real atmospheric signals or artifacts of the star's temperamental surface? The analysis took over a year, not because anyone was slow, but because extracting truth from ambiguous data requires painstaking work. This ambiguity reveals something important about the current state of exoplanet science. We've reached a frontier where the most interesting questions, do rocky planets in habitable zones have atmospheres, push right up against observational limits. The answers exist in the data, but extracting them requires dealing with systematic effects that are comparable in magnitude to the signals we're trying to measure. That's fundamentally different from studying hot Jupiters, where atmospheric signals are strong and stellar contamination is manageable. Webb is working at the edge of what's possible, and that means dealing with uncertainty. The TOI 561b discovery succeeded partly because the planet's extreme conditions actually helped. The atmosphere on this scorching super-Earth produces a large thermal emission signal. The planet glows bright in infrared because it's so hot. That makes detection easier than trying to spot a temperate atmosphere through transmission spectroscopy. The temperature difference between a bare rock and a rock with an atmosphere also proved diagnostic. If TOI 561b had no atmosphere, its day side should reach about 4,900 degrees Fahrenheit. Observations showed only 3,200 degrees, suggesting atmospheric heat redistribution. That 1,700-degree discrepancy provided compelling evidence without requiring detection of specific molecules. But you can't use that technique for temperate planets. A world at 20 degrees Celsius doesn't glow bright enough in infrared for Webb to easily detect thermal emission. You're forced back to transmission spectroscopy, watching transits, dealing with stellar contamination. The cooler the planet, the harder the measurement. That's why confirming atmospheres on truly habitable zone worlds takes years of observations rather than months. LHS 1140b represents perhaps the best near-term opportunity, but even there, the timeline stretches over multiple years. The planet is only visible to Webb during certain windows, a maximum of 8 observations per year. Each observation adds data, building signal to noise gradually. Current hints of a nitrogen-rich atmosphere need confirmation. That requires at least 1 more year of observations, probably 2. Detecting carbon dioxide, crucial for assessing habitability, will take 2 or 3 additional years beyond that. We're talking about a half-decade campaign to characterize a single world. Some scientists wonder if we're being too conservative, too careful about claiming atmospheric detections. After all, the tentative signals from TRAPPIST-1e and LHS 1140b look compelling to many researchers. Why not announce atmospheres now and refine details later? The answer comes down to scientific credibility and the history of exoplanet claims that didn't hold up under scrutiny. Researchers remember the excitement over claimed biosignatures on Venus, phosphine detections that subsequent analysis cast into serious doubt. They remember controversies over methane on Mars. The exoplanet community has learned to be cautious, to demand high statistical confidence before making definitive claims, especially for potentially habitable worlds where public interest runs high. That caution extends to the dimethyl sulfide detection on K218b. If confirmed, DMS would be extraordinary, a molecule produced almost exclusively by life on Earth, detected in the atmosphere of a distant world, but if confirmed, carries enormous weight. The initial detection had marginal statistical significance. Non-biological processes could potentially produce DMS in certain environments. The planet itself, a sub-Neptune rather than a true rocky world, might not even have a solid surface, complicating habitability arguments. Researchers are pursuing follow-up observations, but they're being careful not to oversell a tentative detection as proof of life. This conservative approach frustrates some observers who want answers now, but it reflects hard-won wisdom. Extraordinary claims require extraordinary evidence, and atmospheric characterization of distant worlds produces subtle signals easily confused with systematic effects. Better to be right eventually than wrong immediately. The archival nature of Webb observations provides some comfort. Every dataset is preserved and publicly available. If someone develops a better analysis technique in 5 years, they can reanalyze old data, potentially extracting stronger signals or correcting for effects the original researchers missed. That's already happening with some early Webb observations. Researchers revisiting targets with improved stellar contamination models, finding clearer signals than initial analyses revealed. This iterative refinement will continue throughout Webb's operational life and beyond. The telescope's broader impact on planetary science extends beyond individual detections. Even null results, confirming that certain planets lack substantial atmospheres, provide valuable data. Learning that TRAPPIST-1b and 1c are likely barren rocks tells us something important about atmospheric retention around red dwarfs. It constrains models of stellar radiation effects, guides expectations for other systems, helps prioritize future observations. Every measurement adds to our understanding, regardless of whether it reveals the atmosphere we hoped to find. Webb has also uncovered completely unexpected phenomena that weren't on anyone's prediction list. The diamond-forming exoplanet PSRJ 2322-2650b, a Jupiter-mass world with a helium and carbon-dominated atmosphere orbiting a pulsar, challenges formation theories in fundamental ways. Nobody predicted such an object would exist, let alone that it would form diamonds in its atmosphere through carbon condensation. The water ice clouds on Epsilon Indi AB similarly surprised researchers, forcing revisions to atmospheric models that hadn't included cloud physics for certain temperature regimes. These surprises underscore an important point about exploration. You can't predict what you'll find when you look at new types of objects with unprecedented sensitivity. Webb is revealing that planetary atmospheres exhibit far more diversity than models anticipated. Hot Jupiters, warm sub-Neptunes, temperate rocky worlds, ancient lava balls, each category presents its own surprises. That diversity reflects the incredible range of formation conditions, evolutionary pathways, and environmental influences across different planetary systems. The observational campaigns continue. By mid-2026, Webb has accumulated nearly 4 years of exoplanet data spanning dozens of targets. Some observations have produced clear detections, molecules identified with high confidence, atmospheric properties well constrained. Others remain ambiguous, awaiting additional data or improved analysis techniques. Still others have definitively ruled out certain atmospheric compositions, narrowing the possibilities. The overall picture is one of steady progress rather than breakthrough moments, with understanding accumulating gradually as datasets grow. Resource allocation remains a constant challenge. Webb's time is precious. Thousands of proposals compete for limited observing hours. Exoplanet observations often require long integration times and multiple visits, consuming significant fractions of available time. Program committees must balance competing priorities, characterizing promising habitable zone candidates versus surveying diverse planet types, following up tentative detections versus exploring new targets, depth versus breadth. These decisions shape what gets observed when, affecting which questions get answered first. The community has largely prioritized rocky planets in or near habitable zones when circumstances allow, but practical constraints matter. If a potentially habitable planet orbits an extremely active star, making atmospheric detection nearly impossible, should Webb spend hundreds of hours trying? Or focus instead on a hotter planet with clearer signals that at least advances atmospheric science, even if it's not habitable? These pragmatic considerations influence observing strategies, sometimes leading to targets that seem less exciting, but offer better prospects for actual detection. The K218b controversy illustrates another dimension of these challenges. The planet is scientifically fascinating, a sub-Neptune with a hydrogen-rich atmosphere containing carbon-bearing molecules. But is it habitable? Probably not in any conventional sense. The Hycean world concept, hydrogen-rich atmospheres over liquid water oceans, remains speculative, with significant theoretical objections. Yet K218b attracts enormous public attention because of the potential biosignature claim, creating pressure to allocate observing time, even though other targets might offer clearer paths to answering habitability questions. Scientists must navigate these pressures while maintaining scientific integrity. Public engagement is valuable. People should care about the search for life beyond Earth. But overselling tentative results or allowing hype to drive observing priorities can undermine the methodical work required to actually answer these profound questions. The balance isn't always easy to strike, especially when funding agencies and institutions respond to public interest. Looking forward, the next few years will likely bring more definitive results for several key targets. LHS 1140b will accumulate enough observations to confirm or rule out its tentative nitrogen atmosphere. TRAPPIST 1e will either emerge as a clear atmospheric detection or remain ambiguous, indicating stellar contamination is too severe for current techniques. Other systems, perhaps less famous but observationally favorable, will yield their secrets as datasets grow. Each result will refine our understanding of where and how atmospheres form and persist around rocky planets. The technical limitations aren't just theoretical concerns, they're determining which questions actually get answered. Webb's instruments excel at mid-infrared wavelengths, perfect for hot planets that glow brightly against their stars. But temperate worlds emit far less infrared radiation, making detection exponentially harder. A planet like Earth around a Sun-like star would produce signals too faint for Webb to reliably detect, no matter how long you observe. That's why the focus stays locked on red dwarf systems, smaller, cooler stars, where even temperate planets produce stronger signals relative to their host. This creates an interesting bias in our emerging picture of planetary atmospheres. We're not sampling randomly across all planet types. We're sampling what's detectable, which skews heavily towards small stars and specific orbital configurations. The conclusions drawn from Webb's observations necessarily reflect these selection effects. When we eventually develop capability to study Earth-like planets around Sun-like stars, the atmospheric diversity might look completely different. Current observations are building understanding within constraints imposed by technology and physics. Consider TOI 561b, that ancient lava world with its unexpected atmosphere. The discovery fundamentally challenges assumptions about atmospheric retention around ultra-hot planets. Scientists thought any atmosphere on such a scorching world would evaporate within millions of years. Yet here's a planet billions of years old, maintaining substantial air. The atmosphere exists in dynamic equilibrium with the magma ocean below, gases continuously exchanging between surface and sky, creating a system unlike anything in our solar system. The temperature measurements tell the real story. A bare rock at TOI 561b's distance should reach 4,900 degrees Fahrenheit on the day side. Webb measured 3,200 degrees instead. That 1,700 degree difference requires explanation. Heat is being transported somehow from the permanent day side to the eternal night. Only an atmosphere can accomplish that redistribution efficiently enough to match observations. The discovery opens entirely new research directions, studying planetary interiors by analyzing their atmospheres, understanding how volatile rich worlds evolve differently than Earth, exploring atmospheric chemistry at extreme temperatures. What makes TOI 561b particularly valuable scientifically is its age. The star is twice as old as our Sun, formed when the universe contained far fewer heavy elements. This planet represents an ancient class of worlds that dominated earlier cosmic epochs. If atmospheres can persist under such extreme conditions for billions of years, that expands the range of environments where complex atmospheric chemistry might occur. It's not directly relevant to habitability. Nothing lives on a lava ocean, but it reveals unexpected resilience in planetary systems. The observations required serious commitment. Webb monitored TOI 561b for 37 hours across nearly 4 complete orbits. That's substantial telescope time for a single target, illustrating the investment needed to characterize challenging atmospheres. Multiply that across dozens of interesting targets, and you understand why progress accumulates gradually rather than arriving in sudden breakthroughs. Each definitive detection represents months of observation, analysis, and peer review. Meanwhile, the eyeball planet concept for LHS 1140b captures imagination while highlighting fundamental questions about habitability on tidally locked worlds. If the planet has sufficient atmosphere and surface water, climate models predict heat redistribution would melt ice on the star-facing side, creating a bullseye ocean perhaps 4,000 kilometers across. Surface temperatures in that ocean's center might reach comfortable 20 degrees Celsius, warmer than most Earth oceans. But that scenario requires multiple assumptions stacking perfectly. First, the planet needs substantial atmosphere. The nitrogen hints remain tentative, requiring confirmation through additional observations. Second, it needs significant surface water, supported by density measurements suggesting 9 to 19% water content by mass, but not yet proven. Third, the atmospheric composition must produce enough greenhouse warming to maintain liquid water while not creating runaway effects. And fourth, the ocean must remain stable over geological timescales, despite extreme temperature gradients between the illuminated and dark hemispheres. Each assumption carries uncertainty. The nitrogen detection sits at the edge of significance, real signal or instrumental artifact. Additional observations will clarify, but Webb can only visit LHS 1140b8 times annually due to orbital geometry. Building sufficient data to confirm atmospheric composition requires multi-year campaigns. Carbon dioxide detection, crucial for understanding greenhouse warming, needs even longer baseline. We're looking at 2028 or beyond before definitive atmospheric characterization completes. That timeline frustrates researchers and public alike, but it reflects physical reality. Temperate planets produce weak signals demanding long integrations and multiple transits to achieve statistical confidence. Patience isn't optional. It's the price of studying worlds that might actually be habitable. The slow accumulation of data tests discipline, but rushing to conclusions based on marginal detections would be scientifically irresponsible. Better to wait for clarity than claim discoveries that later evaporate under scrutiny. The TRAPPIST-1 system embodies these tensions perfectly. 7 Earth-sized planets, 3 in the habitable zone, orbiting a nearby star. It's almost too good to be true. And perhaps it is. The innermost planets, B and C, show no evidence of substantial atmospheres despite multiple observations. The habitable zone candidates remain ambiguous. TRAPPIST-1e might have atmosphere, might be bare rock. Current data genuinely can't distinguish between scenarios because stellar contamination overwhelms the signal. This isn't failure, it's honest assessment of observational limits. The star's variability creates apparent spectral features that mimic atmospheric signals. Distinguishing real planetary signatures from stellar artifacts requires comparing multiple planets, modeling stellar activity patterns, and accumulating observations across different epochs. The analysis techniques are sophisticated, involving Gaussian process models that attempt to separate time-varying stellar components from stable planetary signals. But when stellar contamination approaches or exceeds the atmospheric signal strength, even advanced methods struggle. The comparative approach, observing TRAPPIST-1b alongside TRAPPIST-1e, helps somewhat. If both planets show similar spectral features, those features probably originate from the star rather than planetary atmospheres, since B almost certainly lacks air. Features appearing only in E's spectrum might be genuine atmospheric signals. This logic is sound, but execution is complicated by different orbital geometries, varying stellar activity between observation epochs, and the possibility that both planets have thin atmospheres with similar compositions. Scientists are essentially trying to extract planetary whispers from stellar shouts. It's possible, but it requires patience and accumulated data. The TRAPPIST-1 campaign will likely extend through the rest of the decade, with definitive atmospheric detections, if they occur, arriving gradually rather than suddenly. Each observation refines understanding incrementally, narrowing possibilities without necessarily providing final answers. The K2-18b situation illustrates different challenges, interpreting complex data from an unusual planet type. The sub-Neptune clearly has atmosphere, and that atmosphere clearly contains carbon-bearing molecules, including methane and carbon dioxide. The controversial dimethyl sulfide signal, if confirmed, would be extraordinary. That molecule is produced almost exclusively by biological processes on Earth. But almost exclusively isn't exclusively, and K2-18b isn't Earth. The planet's classification as a potential Haitian world, hydrogen atmosphere over liquid water ocean, remains speculative. Theoretical objections exist. The hydrogen envelope might be too thick and hot to allow liquid water surfaces. The planet might lack solid surfaces entirely. The pressure-temperature conditions might prevent stable oceans, even if water exists. These aren't minor quibbles. They're fundamental questions about whether the entire Haitian concept is physically viable. Additional observations are scheduled, using different instrument modes and longer integration times to either confirm or rule out the DMS signal. But even confirmation wouldn't automatically imply biology. Non-biological production pathways exist, particularly in exotic chemical environments unlike Earth's. Distinguishing biological from abiological sources requires understanding the full atmospheric context: pressure, temperature, other molecules present, photochemical processes, possible geological sources. This complexity explains why scientists resist declaring biosignature detections based on single molecules. Real biosignature identification requires comprehensive atmospheric characterization, ruling out abiological explanations, and demonstrating chemical disequilibrium consistent with biological metabolism. Webb can contribute to that process, but it can't complete it alone. These questions will likely require next-generation telescopes with higher sensitivity and spectral resolution. The exotic worlds discovered, diamond-forming gas giants, forbidden planets with unexpected compositions, atmospheres evaporating in real time, remind us how diverse planetary systems actually are. Earth's atmosphere isn't some universal template that most planets follow. It's one data point in vast parameter space. Most planets probably have atmospheric chemistry completely unlike anything in our solar system. Some may have no atmospheres at all. Others might have air so thick and hot it transitions to supercritical fluids without clear boundaries between atmosphere and surface. This diversity isn't obstacle, it's opportunity. Every weird planet teaches something about formation physics, atmospheric chemistry, or planetary evolution. The Jupiter-like world with water ice clouds challenges models that assumed such clouds couldn't form in exoplanet atmospheres. The ultra-hot Jupiter losing helium atmosphere demonstrates mass loss processes in extreme environments. Each discovery fills gaps in theoretical frameworks, revealing which models need revision and which processes dominate under different conditions. The observational campaigns will continue expanding Webb's exoplanet dataset through the late 2020s. Some targets will yield clear detections, molecules identified with high confidence. Others will remain frustratingly ambiguous, awaiting improved techniques or complementary observations from other facilities. Still others will definitively rule out certain atmospheric types, narrowing possibilities even without positive detections. All contribute to the emerging picture of atmospheric diversity across planetary populations. Resource allocation will keep generating difficult decisions. Every hour spent on one target is an hour unavailable for others. Program committees must weigh competing factors: scientific importance, detection probability, public interest, instrumental efficiency. Sometimes the most scientifically valuable observations aren't the most exciting publicly. Sometimes the most detectable planets aren't the most interesting scientifically. Balancing these considerations while maintaining focus on core scientific questions requires discipline and clear priorities. The Nancy Grace Roman Space Telescope, launching in the late 2020s, will complement Webb's capabilities by surveying wider fields and identifying new candidates for detailed spectroscopic follow-up. That partnership between wide-field surveys and deep spectroscopy represents the productive model going forward, each facility doing what it does best, results feeding into the other's observing programs. Webb characterizes individual targets in exquisite detail, while Roman finds those targets across larger sky areas. Looking across Webb's first 4 years of exoplanet science, the pattern is clear: steady progress accumulating through systematic observation rather than dramatic breakthroughs arriving unexpectedly. That's actually how most science advances: incremental understanding building toward comprehensive pictures rather than sudden revolutions. The revolutionary moments do occur, but they're usually built on extensive groundwork laid through patient, methodical investigation. The search for habitable worlds and potential biosignatures continues with appropriate scientific caution, balanced against legitimate excitement about possibilities. we're genuinely closer to characterizing rocky planet atmospheres than ever before. We have tentative detections that might represent Earth-like air on temperate worlds. We're developing techniques to distinguish stellar contamination from planetary signals. We're building the observational and theoretical framework needed to eventually identify biosignatures if they exist. But we're also learning humility. Nearly every observation reveals unexpected complexity. Simple questions produce complicated answers. Planets refuse to fit neatly into predicted categories. The universe, as always, is more creative than our theories anticipate. That humility becomes most valuable when considering how this investigation might eventually conclude. Confirmation of atmospheres on worlds like TRAPPIST-1e or LHS-1140b would represent historic achievements, but they wouldn't answer the ultimate question. Finding nitrogen and carbon dioxide tells you about atmospheric chemistry, not biology. Detecting water vapor confirms potential habitability, not actual inhabitants. Even identifying molecules like dimethyl sulfide, which on Earth comes almost exclusively from living organisms, wouldn't constitute proof of life elsewhere. The gap between detecting interesting molecules and confirming biosignatures remains enormous. Life produces countless chemical signatures, but non-biological processes can mimic many of them. Photochemistry driven by stellar radiation creates complex molecules. Volcanic outgassing releases diverse compounds. Atmospheric circulation patterns generate surprising chemical gradients. Distinguishing biology from clever chemistry requires not just detecting molecules, but understanding their context, their abundances, their spatial distributions, their temporal variations, their thermodynamic plausibility given local conditions. This means the discovery timeline stretches much further than casual observers might expect. Suppose Webb definitively confirms an Earth-like atmosphere on a temperate rocky planet by 2027 or 2028. That achievement would deserve celebration, but it would mark the beginning of detailed characterization rather than the end. Identifying individual molecules and measuring their abundances might require another several years of observation. Understanding whether those abundances indicate biological processes could take even longer, potentially requiring observations from multiple facilities using different techniques. The Roman Space Telescope, launching in the late 2020s, will contribute significantly to this extended investigation. While Webb excels at detailed spectroscopy of known targets, Roman will survey much larger sky regions, discovering new exoplanet candidates at unprecedented rates. Some of those candidates will inevitably prove more favorable for atmospheric characterization than currently known systems. The partnership between survey missions finding targets and spectroscopic missions characterizing them has driven astronomy's most productive eras. Think how Hipparcos astrometry enabled targeted follow-up that discovered countless new phenomena. That collaborative model extends beyond space telescopes. Ground-based, extremely large telescopes currently under construction, the 30-meter telescope, Giant Magellan Telescope, Extremely Large Telescope, will contribute complementary observations. Their enormous mirrors collecting vast amounts of light will enable high-resolution spectroscopy, revealing details Webb cannot access. Adaptive optics systems correcting for atmospheric turbulence will produce sharper images. Different instrumental capabilities will probe different wavelength ranges and atmospheric phenomena. The timeline for answering profound questions about life beyond Earth thus stretches across decades, not years. Webb represents one crucial phase in multi-generational investigation. Its observations will inform designs for future missions specifically optimized for biosignature detection. Those missions, launching perhaps in the 2030s or 2040s, will build on Webb's discoveries, targeting the most promising candidates with instruments designed from the beginning for that specific purpose. This extended timeline might disappoint those hoping for rapid resolution, but it reflects the genuine difficulty of the challenge. We're not looking for obvious beacons announcing life here. We're searching for subtle chemical imbalances that might indicate biological processes in environments we barely understand, on worlds we can only observe indirectly. The fact that this seems feasible at all represents extraordinary progress compared to even 20 years ago, when exoplanet atmospheres seemed completely beyond observational reach. The psychological dimension of this search deserves consideration. How do you maintain scientific rigor and appropriate skepticism while investigating questions that carry such profound implications? How do you balance the excitement that drives public support and funding with the caution that prevents premature conclusions? How do you communicate tentative, ambiguous results to audiences hoping for definitive answers? These questions don't have simple solutions. They require ongoing negotiation between scientific communities, funding agencies, media organizations, and public audiences. Webb's exoplanet results have generally navigated these tensions successfully. Papers clearly state uncertainties. Press releases emphasize tentative nature of detections. Follow-up observations are planned to test initial findings. Maintaining that disciplined approach will become more challenging if and when observations start approaching genuine biosignature detections. The possibility of false positives represents a serious concern. Imagine announcing detection of dimethyl sulfide or some other potential biosignature molecule, only to discover through subsequent observations that non-biological processes explain the signal. The reputational damage to researchers would be significant, but the blow to public confidence in scientific institutions could be worse. The scientific community remembers the controversial Mars meteorite announcement in 1996, which claimed possible fossil evidence of ancient Martian life based on microscopic structures that subsequent research attributed to non-biological processes. That cautionary example suggests several principles for handling potential biosignature detections. First, require extremely high statistical significance, not just 3 sigma or even 5 sigma detections, but overwhelming evidence that leaves minimal room for alternative explanations. Second, demand independent confirmation from multiple instruments, multiple observation techniques, multiple research teams. Third, extensively model non-biological processes that might produce similar signals before claiming biological origin. Fourth, clearly communicate remaining uncertainties and alternative interpretations when presenting results publicly. Following those principles necessarily slows the path from initial detection to confirmed biosignature, but that delay protects the integrity of conclusions. Better to take years carefully ruling out alternatives than to rush announcements that might later require embarrassing retractions. Meanwhile, Webb's broader impact on exoplanet science extends beyond individual atmospheric detections. The accumulated dataset of dozens of characterized atmospheres across different planet types and orbital configurations enables statistical studies previously impossible. Researchers can now examine how atmospheric composition correlates with stellar properties, orbital distance, planet mass, planet radius, system age, stellar metallicity, and numerous other parameters. Those statistical patterns reveal formation and evolution processes operating across planetary populations. They test theoretical predictions about which planets should retain atmospheres versus losing them to stellar wind stripping or hydrodynamic escape. They constrain how atmospheric composition evolves over billions of years through processes like photochemistry, atmospheric escape, volcanic outgassing, and potential biological modification. The characterization of exotic atmospheres on worlds utterly unlike anything in our solar system. The helium-carbon atmosphere on PSRJ 2322-2650b, the water ice clouds on Epsilon Indi AB, the magma ocean atmosphere on TOI 561b, expands the known diversity of planetary environments. Each weird planet teaches something about the range of possibilities allowed by physics and chemistry under different conditions. This diversity matters practically as well as intellectually. Understanding what makes planets habitable requires knowing what makes them uninhabitable. Every airless rocky world, every hydrogen-stripped sub-Neptune, every ultra-hot Jupiter-losing atmosphere teaches lessons about processes that prevent habitability. Those lessons inform the search for habitable worlds by clarifying which planetary characteristics actually matter for maintaining stable, temperate conditions over geological timescales. The investigation also reveals how much remains unknown about atmospheric physics and chemistry. Cloud formation in exoplanet atmospheres remains poorly understood. Models often omit clouds because they're difficult to simulate, but observations keep finding them. Photochemical networks producing complex molecules from simpler precursors involve thousands of reactions whose rates and products depend sensitively on temperature, pressure, radiation environment, and catalytic effects. Atmospheric circulation patterns, transporting heat and redistributing chemicals, operate differently under various rotation rates, stellar heating patterns, and planetary parameters. Each observation, confronting expectations or contradicting predictions, indicates gaps in theoretical understanding. Those gaps represent opportunities. They point toward phenomena requiring new physics, new chemistry, or better models, incorporating complexity, current theories neglect. Progress comes not just from confirming predictions, but from finding mismatches that demand explanation. Looking toward the future, several developments will shape the next phase of exoplanet atmospheric science. Improved data analysis techniques will extract more information from existing observations, potentially revealing subtle signals currently hidden in noise. Machine learning algorithms trained on synthetic spectra might identify atmospheric features human analysts miss. Better stellar models will help separate stellar contamination from planetary signals in transit observations. Longer observing campaigns accumulating dozens or hundreds of transits for individual targets will achieve signal-to-noise ratios, enabling detection of trace atmospheric constituents. If LHS 1140b does have a nitrogen-rich atmosphere with surface oceans, confirming that will require multi-year campaigns accumulating sufficient data to detect carbon dioxide, water vapor, and potentially other molecules at the concentrations expected for habitable environments. Some targets will require entirely new observational approaches. Direct imaging of reflected light from temperate rocky planets remains beyond Webb's capabilities, but might become possible with future missions equipped with coronagraphs or star shades blocking host starlight. Those observations would reveal different information than transit spectroscopy. Albedo variations indicating surface features, potential seasonal changes, possibly even hints of vegetation red edge or other surface biosignatures. The pathway from current tentative detections to confirmed biosignatures on habitable worlds thus involves technological development, observational campaigns, theoretical advancement, and careful analysis spanning many years. No single observation will provide definitive answers. Instead, accumulating evidence from multiple techniques will gradually strengthen or weaken the case for biological processes on specific worlds. That gradual accumulation of evidence characterizes most scientific progress. Revolutionary moments do occur, but they typically build on extensive preparatory work. Webb's exoplanet observations represent crucial steps in multi-decade investigation that might eventually confirm life beyond Earth. Or they might reveal that habitable worlds are rarer than hoped, that atmospheric retention around red dwarfs proves more difficult than expected, that the universe contains incredible diversity of lifeless worlds, but few living ones. Either outcome teaches profound lessons about our place in the cosmos. Discovering we're alone despite billions of potentially habitable planets would raise fascinating questions about the origin of life and the frequency of successful abiogenesis. Discovering we're not alone would reshape human self-understanding in ways difficult to predict. For now, we're in the exploratory phase, mapping the landscape of exoplanet atmospheres, identifying the most promising targets, developing the techniques and technologies needed for definitive characterization. Webb has opened the door to this investigation, revealing that characterizing rocky planet atmospheres lies within reach of current capabilities, while simultaneously demonstrating how challenging the task remains. The tentative hints of atmospheres on temperate worlds justify continued investigation, while appropriately not over-promising imminent discoveries. That balance between possibility and caution defines responsible science addressing questions whose answers matter profoundly while remaining genuinely uncertain. We're watching this unfold in real time, not through sudden revelations that rewrite textbooks overnight, but through the patient accumulation of data that might eventually answer humanity's oldest question: are we alone? The discoveries Webb has made, TOI 561b's impossible atmosphere, LHS 1140b's tentative nitrogen signals, the controversial dimethyl sulfide on K2-18b, represent waypoints on a journey with no clear endpoint. Each observation adds pieces to a puzzle whose final image remains obscure. Some pieces fit together smoothly, revealing coherent pictures of atmospheric chemistry and planetary evolution. Others refuse to connect, their shapes suggesting complexity we haven't learned to interpret. Think about what these 4 years have actually accomplished. We've moved from wondering whether rocky exoplanet atmospheres could be characterized at all, to debating the composition of specific atmospheres on specific worlds. We've transitioned from theoretical predictions about atmospheric retention to empirical measurements that challenge those predictions. We've gone from models suggesting where atmospheres might exist to observations revealing they exist in places they shouldn't. That progression matters more than individual detections. The infrastructure being built, observational techniques, analysis methods, theoretical frameworks will outlast any single discovery. Future missions will inherit this foundation, building capabilities that extend what Webb began. Roman will find targets Webb can characterize. Ground-based extremely large telescopes will provide complementary data at wavelengths Webb cannot access. Specialized biosignature hunting missions launching in the 2030s or 2040s will focus on candidates identified through this current investigation. The timeline stretches uncomfortably long for anyone hoping to learn whether life exists beyond Earth during their lifetime. Confirming atmospheres on habitable zone planets requires multi-year campaigns still underway. Detecting potential biosignatures demands even longer observation baselines. Actually distinguishing biological from non-biological sources of interest in molecules that might require capabilities Webb simply doesn't possess, pushing definitive answers into future decades when next-generation telescopes come online. Yet progress continues. Every few months brings new papers analyzing Webb data, refining atmospheric characterizations, constraining possibilities. TRAPPIST-1e will eventually yield to continued observation, either confirming its atmosphere or demonstrating that stellar contamination prevents detection with current techniques. LHS-1140b's nitrogen hints will solidify into confirmed detection or evaporate into instrumental artifacts as datasets accumulate. K218b's dimethyl sulfide will prove real or illusory through follow-up observations already scheduled. These outcomes matter regardless of which direction they point. Confirmed atmospheres on temperate rocky planets would validate decades of theoretical work, predicting such worlds should exist and survive. Null detections would force reconsideration of atmospheric retention mechanisms, perhaps indicating red dwarf planets face harsher radiation environments than models suggest. Either result advances understanding by constraining possibilities. The exotic worlds discovered, diamond-forming gas giants, forbidden planets, magma oceans maintaining thick air, expand the known diversity of planetary environments far beyond what our solar system represents. That diversity isn't noise obscuring the search for Earth-like worlds. It's signal revealing the creative range of planetary formation and evolution operating across different conditions. Every weird planet illuminates some aspect of the physical processes that create and sustain atmospheres, even when those processes operate in regimes we never anticipated. Consider the implications if LHS-1140b does prove to be an eyeball planet with a temperate ocean surrounded by global ice sheets. That configuration, tidally locked world with concentrated habitability in a bullseye region, represents a planetary archetype completely absent from our solar system. If such worlds are common, and if life can emerge in those localized habitable zones, then the number of potentially inhabited worlds might vastly exceed estimates based on Earth analog assumptions. Life might thrive in environments we never thought to consider, expanding the search space enormously. Or perhaps life requires more than just liquid water and moderate temperatures. Maybe it needs global habitability, stable climates over billions of years, protection from stellar flares, specific atmospheric compositions that eyeball planets cannot maintain. The absence of biosignatures on worlds we expect to be habitable would teach crucial lessons about what habitability actually requires beyond the simplified models we currently employ. The universe will answer these questions on its own schedule, indifferent to human impatience. Our role is to keep observing, analyzing, questioning, refining. Webb has demonstrated that characterizing exoplanet atmospheres lies within humanity's technical capabilities. That alone represents extraordinary achievement compared to where the field stood even a decade ago. The detailed answers we seek might require instruments we haven't built yet, but we're learning what questions to ask and which targets to prioritize once those instruments become available. The scientific community has learned hard lessons about premature claims and overhyped results. The phosphine on Venus controversy, the Mars meteorite debates, the numerous exoplanet discoveries later retracted. These experiences instilled appropriate caution when interpreting data at the edge of detection limits. That caution might frustrate public audiences hoping for dramatic announcements, but it protects the integrity of conclusions that ultimately emerge. Better to build slowly toward well-supported findings than to rush toward attention-grabbing claims that crumble under scrutiny. Meanwhile, the observations continue. Webb accumulates data on dozens of targets across diverse planetary types and orbital configurations. Each observation adds to the archive, creating datasets future researchers will mine for insights using techniques not yet invented. The telescope's legacy will extend far beyond its operational lifetime, providing raw material for discoveries decades hence when someone develops a new way to extract information from spectroscopic data. Resource allocation will keep generating difficult choices. Every hour dedicated to one target is an hour unavailable for others. The Time Allocation Committee balances competing priorities, following up tentative detections versus surveying new targets, depth versus breadth, certain results versus higher risk investigations that might yield breakthrough discoveries or might produce null findings. These decisions shape which questions get answered when, affecting the trajectory of the field in ways that won't become clear until years later. The Nancy Grace Roman Space Telescope's launch in the late 2020s will shift the landscape significantly. Its wide-field surveys will discover exoplanets at unprecedented rates, identifying candidates Webb and future spectroscopic missions can characterize in detail. That partnership between discovery and characterization represents the productive model for the next phase of exoplanet science. Each facility doing what it does best, results feeding into complementary observations from other platforms. Ground-based, extremely large telescopes under construction will contribute high-resolution spectroscopy, revealing atmospheric features Webb cannot resolve. Their enormous light-gathering power will enable observations of fainter targets and shorter integration times for brighter ones. Adaptive optics correcting for atmospheric turbulence will produce sharper images and cleaner spectra. The combination of space-based infrared observations from Webb and Roman with ground-based optical and near-infrared observations from ELTs will provide multi-wavelength coverage, revealing atmospheric properties no single facility could characterize alone. This collaborative approach recognizes that no single telescope can answer every question. Webb has specific strengths: unmatched infrared sensitivity, stable space environment, instruments optimized for spectroscopy. But it has limitations too: finite observation time, restricted wavelength coverage, detector noise flaws. Combining data from multiple observatories overcomes individual limitations, building comprehensive pictures of exoplanet atmospheres through complementary observations. The timeline for definitive biosignature detection, if it happens at all, stretches into the 2030s or beyond. Missions specifically designed for that purpose, like the Habitable Worlds Observatory concept, remain in early planning stages. Those missions will benefit from Webb's discoveries, targeting the most promising candidates with instruments optimized from the start for detecting and characterizing potential biosignatures. But they won't launch for many years, requiring patience from scientists and public audiences alike. That patience proves difficult when contemplating questions that resonate so deeply. Are we alone? Does life emerge readily whenever conditions allow? Or are we cosmically unique? Do other worlds harbor biospheres, perhaps even intelligence? These questions connect to fundamental human concerns about meaning, purpose, and our place in the universe. The slow pace of observational astronomy can feel frustrating when measured against the urgency of existential curiosity, yet the investigation proceeds at the pace observations allow. You cannot force stars to align or planets to transit more frequently. You cannot eliminate stellar contamination through sheer determination. You cannot extract signals from noise by wanting answers badly enough. The universe reveals its secrets according to physics and geometry, indifferent to human timelines or emotional investment. What we can control is our approach to the investigation. Maintain rigorous standards for evidence. Demand statistical significance that leaves minimal room for alternative explanations. Pursue independent confirmation through multiple techniques and facilities. Clearly communicate uncertainties and remaining questions when presenting results. Build theoretical frameworks that make testable predictions. Design instruments optimized for questions we actually need to answer, rather than questions we wish we could address. Following those principles produces slower progress than ambitious claims and overhyped results, but the conclusions that eventually emerge carry correspondingly greater weight. The scientific community is learning to navigate the tension between excitement and caution, between public engagement and technical precision, between hope and skepticism. That navigation isn't perfect. Mistakes will happen. Claims will require revision. Interpretations will shift as new data arrives. But the overall trajectory points toward increasingly robust understanding of exoplanet atmospheres and the conditions necessary for habitability. Webb's exoplanet observations represent one chapter in a multi-generational investigation whose conclusion remains unwritten. The telescope has proven that characterizing rocky planet atmospheres lies within human capability, while simultaneously revealing how difficult the task actually is. It has found atmospheres where conventional wisdom said none should exist. It has identified tentative hints of Earth-like air on temperate worlds. It has demonstrated techniques that future missions will refine and extend. And it has shown that the universe contains planetary diversity far exceeding what our solar system represents. Whether any of these worlds harbor life remains unknown. The tentative detections might eventually confirm atmospheres on habitable zone planets, or they might dissolve into instrumental artifacts and stellar contamination. The controversial biosignature candidates might prove real or illusory. The eyeball planet concept might describe a common configuration or an impossible ideal that cannot actually exist. We don't know yet. The data remains insufficient for definitive conclusions, but we're closer than we've ever been to potentially answering these profound questions, not through speculation or wishful thinking, but through systematic observation and careful analysis, not through dramatic breakthroughs arriving unexpectedly, but through patient accumulation of data that gradually constrains possibilities, not through individual heroic efforts, but through collaborative work spanning institutions, nations, and generations. The universe has already written the answers. Life either exists on other worlds or it doesn't. Habitable zone rocky planets either maintain atmospheres or they don't. Biosignatures either appear in exoplanet spectra or they don't. These facts exist independent of human observation or belief. Our task is simply to read what's already written, which requires building instruments sensitive enough to detect faint signals and developing analysis techniques sophisticated enough to interpret ambiguous data. Webb has opened the book to the right chapter. The words remain blurry, requiring patience and effort to decipher. But they're there, waiting to be read. Every observation brings slightly better focus. Every technique refinement clarifies another sentence. Every theoretical advance helps interpret the meaning behind the words. The story these observations tell might not be the story we hope to find. We might discover that habitable worlds are rarer than optimistic projections suggested. We might learn that atmospheric retention around red dwarfs proves more difficult than expected. We might find that while planets exist in habitable zones, something prevents them from maintaining the stable conditions life requires. Or we might discover the opposite, that life emerges readily whenever basic conditions align, filling the galaxy with biospheres we're only beginning to detect. Either outcome transforms human understanding of our cosmic context. Either outcome deserves the careful, methodical investigation Webb has initiated. And either outcome will raise new questions that drive future exploration. Because that's how science works. Every answer reveals new mysteries. Every discovery exposes new ignorance. Every conclusion opens new directions for investigation. The search for life beyond Earth continues, not because we know it exists, but because we don't know it doesn't. The possibility remains open. The question remains unanswered. The universe remains vast and mostly unexplored. And we remain curious, building better telescopes, developing better techniques, asking better questions, inching toward understanding that might eventually reveal whether we're alone or part of something far larger than ourselves. That's where we are. That's where the discoveries have brought us. Not to answers, but to better questions. Not to conclusions, but to possibilities. Not to the end of the investigation, but to a point where the investigation can finally proceed with tools adequate to the task. Webb has shown us the path forward. Now we have to walk it, one observation at a time, one analysis at a time, one discovery at a time, until the picture becomes clear, or until we learn that some questions lie beyond our capability to answer. The universe keeps its secrets well, but it's never stopped us from trying to uncover them. These terrifying, beautiful, impossibly distant worlds, with their unexpected atmospheres and their potential oceans and their chemical mysteries, they're out there right now, orbiting their ancient stars, following the same physical laws that govern our own world. And we're watching them, measuring them, learning from them, gradually assembling the knowledge needed to understand what makes a world capable of hosting life. That investigation defines our era in astronomy. Its ultimate conclusion will define humanity's understanding of its place in the cosmos. But for now, the work continues, the data accumulates, and the universe slowly reveals what it's been hiding all along.